Okay, in this video I'd like to talk to you about the strategy behind the Gram-Schmidt process, which is our method of turning a basis into an orthogonal or an orthonormal basis. So let's start off by looking at this example. Given a vector v and a vector w, compute the projection and v minus the projection. So I'll start off with the projection. We have a formula that says the projection of v onto w is equal to v dot w divided by w dot w multiplied by w. So let's see, in the numerator the dot product is going to be the dot product of these two, so negative 1 times 1 plus 2 times 1. In the denominator we have w dot product w, which would be 1 times 1 plus 1 times 1. And all that is multiplied by the vector w. And so let's see, negative 1 plus 2 would be 1, 1 plus 1 would be 2, so that's 1/2 of the vector 1, 1. And so our projection of v onto w would be 1/2, 1/2. Okay, if we want to find v minus the projection of v onto w, that would be the vector negative 1, 2 minus 1/2, 1/2. And so when we distribute that, we'll have negative 1 minus 1/2, and we'll have 2 minus 1/2, which is going to be the vector negative 3/2, comma, negative 3/2. Okay, so before I talk about the consequence of this, let's draw a picture with these two graphs. Okay, so our first vector is negative 1, 2. That's our v. Our second vector w is 1, 1. We found the projection of v onto w was 1/2, 1/2. So if we drop a perpendicular projection down, it should be this red vector. And next we did v minus the projection. So if we're subtracting the projection, that means we're taking it away. So we're adding a negative projection. And so our answer is going to end in this place, which means that v minus the projection of v onto something else is going to be pointed in this direction. And my artistic ability is kind of failing, but the dotted line here was supposed to be perpendicular to w. This line is parallel to that dotted line, so it should also be perpendicular to w. So the moral of the story is that the original vector we started with, the w, and v minus the projection end up being orthogonal or perpendicular to each other. So 1, 1 and negative 3/2, negative 3/2 is an orthogonal set. And if I wanted to have an orthonormal set instead of an orthogonal set, then that's not that complicated. All I would have to do is find the length of this vector and divide this vector by its length. So the length would be 1 squared plus 1 squared, and then take a square root, so square root of 2. If we divided this by square root of 2, it would be this would be a unit vector. And if I did that for this vector as well, we would end up having an orthonormal set. So that's the general strategy behind Gram-Schmidt. This is kind of paraphrasing what you see in the handout that I provided you guys. If we're given a set, a basis with a whole bunch of vectors, then your first vector in the orthogonal set is just going to be the same as the first one. The second vector is going to be the first one. The second vector is going to be the second vector minus its projection onto what's gone before. So basically the same situation. Given a vector, our second vector, we have to subtract a projection to make it orthogonal. If I gave you a third vector, we would have to subtract projections onto both of the existing two. So that's why in your later Later cases, we end up subtracting more projections, and they're projections onto the vectors you already came up with. And then the last step is, if you wanted to find an orthonormal basis, we would have to divide by lengths. And I'm using a slightly different notation for length of a vector than what you might have seen before. In Calc 3, we just use vertical lines for length of a vector. In this class, we use double lines so that we don't confuse it with determinants.